change the pen color because red is not going to work today. Yeah, that'll be good. All right, any questions on steam before we go into electricity? All right. So let's talk a couple of definitions first. All right. So we're going to be talking about charge, which is in columns. All right. It's the element of electrical energy transport. All right. Then we have current, which is in amperes. All right. Just otherwise known as amps. It's the rate of flow of charge. 1 amp is equal to 1 coulomb per second. Then you have your voltage. That's volts. Energy per charge gained or lost. 1 volt is equal to 1 joule per coulomb. Then you have power, which is in watts. All right. The rate of electrical energy production, transmission or consumption. 1 watt is equal to 1 joule per second, which is equal to 1 joule over a coulomb times 1 coulomb per second. All right. So that's how you get power is equal to voltage times current. All right. Then you have resistance, which is it's opposing the opposition to charge flow measured as the ratio of voltage to current. All right. It's the opposition of flow. It's the resistance to flow. All right. Now there is, just forgot about this. There you go. All right. I will post this on whatever it's called on Blackboard. All right. But basically, this is a good representation of what is actually trying to go on with electricity. All right. Your voltage is what's trying to push your current through. Your current is actually what's going through the wires. Your voltage is that potential energy that's pushing it, that's trying to get it to go through it. And your ohms, which is your resistance, is resisting, it's trying to resist the flow. It's trying to make it harder for them. He's not holding them up in the wire. He's trying to make it harder. All right. If you have that picture in your head, you'll be fine. All right. So let's talk about charge real quick. Charge comes in packets of coulombs. All right, it's either positive or negative. The opposite charges attract. Like charges will repel from each other. 1 electron is equal to negative 1.602 times 10 to the negative 19 coulombs. And 1 negative coulomb is 6.24 times 10 to the 18 electrons. I believe I've said this before, but in your time as an engineer, that number comes up a lot more than you think it would. Not for this class, but just in general. All right, that's 6.25 million trillion electrons. So we have here, it's a little bit of a representation that the electron flow is going to be going opposite of the conventional current. All right, so this is what's actually happening in reality. This is what we say it is happening, or what was believed or perceived to be happening. So the number of coulombs, positive or negative, passing any point in 1 second. That will be current in amperes. Then you have voltage. That's the energy in joules gained or lost by a column of charge moving from point A to point B. Voltage is measured between 2 points versus at a point like current. It's a comparison of the potential. All right. So what you're doing here is you're trying to actually find almost the potential energy between A and B. All right. And that's what you're going to be looking at. Now, if you were to, like it's talking about in this slide, if you were to measure amperes, you would have to place your metering device in line with what's going on. All right. The probes would have to be attached in line with it. You wouldn't have a line where the meter is. Whereas with voltage, you can just take your probes and attach it A to B, call it a day, and you'll get your potential energy there. All right. That's why if you see those metering, those fluke devices that have those claws on it, like this, you know, it's got a couple here, dial here, and a readout, where you could use that. This claw on the metering device is used to find your current, because it uses a couple different readings. It's using, I believe, the electromagnetic current that's coming out from the wire to calculate current. All right, so you don't have to have it in line. You can actually clamp it onto a wire or around a wire, and you can get its actual amperage. All right, another symbol here that we have, this is a battery. All right, sometimes you'll just see the battery written as this. All right, just 2 lines. And my mouse is freaking out again. All right, so you'll see it like that instead of just having a huge amount of cells. That's mostly what you will see. So each column gained is 12 joules through the battery. And then each column gives up 12 joules going through the bulb. So voltage is similar to the energy gained or lost by a cubic inch of fluid moving from point A to point B in a piping system. So we have 12 PSI pump, and you would be reading your potential difference between A and B. All right, each cubic inch is gained 12 pound-inch through the pump, and then you're using this valve to give almost like a restriction. So it's giving up energy as it goes through the valve. So voltage can be thought about as like pressure, and current can be thought about like as fluid flow. So when we talk about power, power is the rate at which energy is delivered to a fluid. So it's pressure times flow. So in SI, it's newtons over meters squared times meters cubed over per second. All right, and that's how we would get watts. So when we talk about power of electricity, the rate at which energy is delivered to or retracted from changes in voltage times current. All right. So you have your voltage times your amps, and that's equal to watts. All right, what's happening here, your joules over columns, your columns over seconds, and your joules over seconds. That's just showing you exactly what's happening behind the scenes. What you guys should know is just that the fact that voltage times your amperage, that's going to be your watts, and watts is power. All right. So in most power systems, the source voltage is constant. The number and types of loads turned on determine the current and the power. All right. That's why you hear everyone talk about the fact that you have 120 voltage source or it's 240. Everyone's talking in voltage. All right. No one's talking in watts. No one's talking in current. All right. Because that can change based on what's happening, what's applied to it. If you were to touch 120 volt source, the current and the power is going to change in the whole circuit, including what's going through your body. That voltage will stay the same. So right now, if we have a 60 watt consumption, so we have 120 times 0.05 amps, we get watts supplied. So we have 60 watts consumed. All right. If we put a 240 watt, all right, so it's 120 times 2.5 because we have to add how many amps are going through. All right. And then here we have 180 watts, 240. All right. So it's 120 times 4 of our amps of our current on each one of these. So that's how we're gaining watts consumed. So the more items turn on, the more power we draw. The longer we let things run, the more energy we consume. So energy is equal to power times time. And we are billed for energy consumption in kilowatt hours. A kilowatt hour is 1,000 watts times 3,600 seconds. All right, and that's equal to 3.6 million joules. So the big thing that we want to see on this entire slide is these points right here. All right. It's the understanding of the more we use, the more lights we have in a circuit, the more power we're going to be drawing. All right. The longer we let these things run, the more energy we're going to consume. All right. It seems second nature, but it's still something that you should keep in your mind as you're going through your electricity. All right. And then the other big thing is that how we are built. All right. So you actually know your power consumption. Like I said, your voltage is going to be the same no matter what. But your actual power consumption is going to change based on how much you use of it. So how much you're turning on your lights, how long you let things run for will change how many wattage and how many of those kilowatts per hour are you using. And they're using that to a dollar amount. That's how they're getting to that, how they know how to bill you, how they know how much you're using just based on the electricity coming through. All right. So what determines how much current a given consumer will draw? It's the resistance. All right, 120 volts is a 60 watt bulb, draws 1/2 an amp because it has a resistance of 240 ohms. All right, so if we have voltage over current is equal to 120 volts over 0.5 amps is equal to 240 ohms. The higher the resistance, the movement of charges, the less current through the device. All right, a bulb with a 360 ohm filament only draws 120 over 360, so a third, and A consumes only 120 times 1/3 is equal to 40 watts. Now we have some basic math equations here. All right. So we basically have two circles here which give us all the relationship, all the math side of what we would want to remember. So you have P over V times I. All right, and V is I over R times R. Sorry. So how we would do this and how we would use what we're looking for is we would basically put your hand, you draw this out, you put your hand over current. So what you would have is that you would have power over voltage is equal to current. All right. And if you were looking for power, put your hand over power, you have voltage times current. All right. And then vice versa over on this side. All right. So a quick example here, if you're looking for current in this example, you have 1200 over 120. So you do 1200 divided by 120. You would get 10. All right. And then in this example over here, it's using the same thing, but you would want to try and find your resistance. So you're going to be using voltage over your current, and the current you just got in this problem over here, you would do 120 over 10, and that's going to be equal to 12. All right, and that's how you find your resistance. All right. So another example, you can go backwards with it. So voltage over resistance, so you have 12 volts over 0.8 ohms. You get 15 as your current. So if you need to find your power, you go 12 times 15, and that gets you 180. All right. While we take a 15-minute break, come back at 10:05. All right. Before we go into DC currents, everything like that. All right. Just as a quick reminder, everyone, the for the test and for the quiz, for tomorrow's quiz, you're going to need a calculator. All right. So for the last, for the quiz, exam 3, and the final, bring a calculator with you. All right. So DC current. DC simply means constant. All right. Current flows in only one direction. The DC voltage remains at a nearly constant level. Batteries are a DC voltage source. DC generators are just simply a generator. Is a voltage source. Rectifiers, which basically converts AC to DC. All right. DC voltage sources are basically, they're just kind of like centrifugal pumps. Near constant pressure with flow determined by connected system elements. All right. So direct current, basically remember that you just have a flow of electrons constantly going through your wire. All right. So if we look at an automotive one, all right, what we have is basically our motor. We have our alternator. All right, we have our rectifier. And basically that's our voltage regulator that's turning it in from a DC current to an AC. All right, we have our battery. We have our ignition circuit, spark plugs, everything that runs off of it, headlamps, radios. So when we close the ignition, we're running off of our battery and we're going into our spark plugs. All right, that starts up the vehicle. The ignition is left off. And now instead of using the battery to run the spark plugs, what you're using now is you're using your actual alternator, and that is going to be charging the battery and also going into your spark plugs. Because what we have here is a parallel circuit. All right, this is not a series circuit. So each one of these branches I can take away and cut into that spark plug line, and you will still have current going through and charging your battery. All right, just how what you have here, your spark plug line is running, but your headlamps are off, your radio is off, your signals, everything else is off, but you're still having flow going through your spark plugs. This is how a parallel circuit works. Each individual piece of component has its own line going back to your ignition, back to the power source. All right, so if you turn on your headlamps, you now have power going to your headlamps. Same with your radio, and same with anything else that you power on in your car. All right. They all go to ground, and it basically returns on the chassis. So the chassis is the ground for the vehicle. All right. So, fun fact here. What is knowing this now, if you were to have, what would show that your battery is dying? If you have a bad battery, would it be would you just kind of die while driving around? Will the car die, or would the car not be able to start? Would you need what is known as a jump?
It wouldn't start.
All right. If you have the way you can tell if you have a bad battery is that you wouldn't be able to start the vehicle in the first place. So you really wouldn't be able to tell during driving around. All right. If you're able to drive around and continue to move the vehicle and it's not dying as long as it's running, it's because your alternator is sending power out to your spark plugs and it's charging your battery. But as soon as you turn the vehicle off, and now you need the battery to start the car and to like actually use the electricity to run your spark plugs. If that doesn't turn the vehicle over and that doesn't start your car, that's how you can tell you have a bad battery. So if you have a bad alternator, the way you can tell that is if you're driving around and the vehicle just slowly will peter out and die. All right. And that's because what's happening is that your battery has a charge to it and you were using the battery instead of having the alternator charge the battery and run all of your spark plugs, headlamps, all that kind of things. It's basically the battery is going to be running your spark plugs. The battery is going to be running everything. And that's why it will slowly die. And all of a sudden the vehicle just won't run anymore. All right. So if we look at our power source on the TSES, there's a couple things we have. All right. We have ship's AC power. All right. So we have alternating current. Did the alternator directly connect to the engine? Yeah, the alternator is directly running off of the engine via pulley. Okay. So let's take a look at what we have here. So we have AC power going into rectifier. All right. And we have voltage DC on this side of it. We have 3 switches. Those are a symbol for a switch, each one of those. And we have our general alarm. All right. So we have, the one up on the bridge, the one down on the quarterdeck, and then the third one. I cannot for the life of remember me where it is off the top of my head. Let's just say it's down the engine room. All right. If you were to close any singular one of those, you would gain power going through that switch and into the general alarm, and thus it will be sounding the general alarm. All right. But if you don't have power at that moment, what you would need is a set of batteries. All right. An AC power source is only as good as when you actually have that power source. So most times when you need that general alarm is when you're going to have no power. You might have a fire in the engine room, all these other things that might be happening. So a good thing to have is backup batteries. And you're basically going to be able to charge these batteries the entire time while these switches are in an open state. All right, and I use the term open because you're going to have an open switch where there is no current flowing. All right, so that's going to be an open switch, and a closed switch is going to look like this, where it's physically closed, and that's going to allow current to go through. All right, I know it's backwards from valves, but an open switch is where no current is flowing, and a closed switch is where current will flow and you'll have power. All right. So when these switches are open, you'll be able to still charge all of your batteries. So in the case that if you have no power and you need to turn on your general alarm, let me get rid of some of this. So you lose ship's power, you can use your batteries to power your general alarm still. All right. So we have two 24-volt DC systems on the TSES. We have ship's AC power coming in. We have our general alarm circuit, and we have our internal communication circuit. So our navigation instruments, etc., any radios, things like that. We also will have battery banks that will be charging during normal operation. All right. So normal operation will consist of these battery banks being charged. And then when we have no current coming into those battery banks, we will go into emergency situation automatically where these batteries will start to output a current. They will output electricity. All right. So question, how did this battery charge? There are 2+ sides. Which slide are you talking about? This slide or the one after it? Oh, so you're talking about how these two charge and these two are charging? Okay. So basically the question is that how are these sets of batteries charging? Where you have one set in series here, we can kind of look at them as one battery, and then you have a set over here. And basically they're operating in series where they're one after each other, where they're dependent on one working, where if one of these batteries doesn't work, this one won't get a charge. So that's a series run. So if we look at this, what's happening is you have your current flowing in here, and it's going down through this wire and it splits. All right. So it's basically going to be splitting and charging both sides at the same time. And then they come back and they're going into a ground together. All right. Because the rectifier and the regular also has a plus in on that side. What do you mean by that? Are you meaning that you have, how can you charge it when you have a positive and positive here? Okay. That's basically, all right. So what's happening here is how it's actually just going to be lined up for charging. All right. And the question is why, how can you have something charged when you have a positive here, positive here, positive here? All right. Basically with that is that what you need is you need to have almost like your, the way it's going to be charged is that you have to almost reverse what you would normally conceive of like flow inside with your batteries. All right. And what you're doing is it's almost like you're trying to like pump up like a reservoir, but it's a reservoir in reverse, and you're kind of like trying to reverse flow it through it. All right, that's how these are being charged that way. All right, you're almost pushing, you're almost kind of like trying to push a charge and reverse it and trying to like, trying to think of an analogy. It's almost like what I would say is like almost like a water bottle, where if water bottle only has one way in, but in order to charge up that water bottle of water, is you only have to, you're going to be charging it through the top of what you would be drinking out of. But then as soon as you would want to drink out of it, it's going to be coming out of the same port, and that's where your current flow is going to be coming out of. But the only way in is in that direction. All right, it's almost the same idea, is that current is trying to be pushed in and you're charging it all through. That's what's happening in there. All right. This won't be the first time you're going to hear about battery charging in your engineering career. All right. And that's not going to be expected to know for the quiz or the test. All right. So as we talked about, we have our normal situations where we're just charging the batteries. And then when we go into our emergency situation, what we're going to be doing is we're going to be pulling any of our current out of the batteries. Automatic switch. It's not like we have to go over to it and push a button. All right. These things will automatically go into this scenario. So if we talk about alternating current, what we have is what we started with DC, is that we just have that constant flow. All right, it's like a water hose that's just shooting out water constantly. The water that was at the spigot a few minutes ago is now at the end of the hose now. All right, but with alternating current, the opposite is almost happening. You have almost the same amount of electrons just kind of shifting back and forth inside of the pipe. All right. So AC refers to sinusoidal pattern of changing values. AC voltage reverses polarity according to this pattern. All right, so the AC is just basically going up and down on a sine wave. All right. So AC current reverses direction according to this pattern. So the basically, if you were to look at like AC lights, if you were to slow it down enough, you would actually see flickering. And that flickering would actually be the sine wave and the changing of your current going back and forth. All right. So a couple definitions for AC. You have your peak values. They go in both of the positive and the negative, or effective. All right. Your effective value is the nominal voltage and current are effective values. All right. So your peak is, it's basically your effective is your peak over the square root of 2. All right. So this effective value is going to be like your 120 volt. All right. The period is the time in between two peaks. All right. On the same side. It won't be to this point here. All right. Frequency is the number of cycles completed in 1 second. All right. So frequency is equal to 1 over T. And that's measured in hertz. So the standard frequency in the United States is 60. All right. I will be posting a video onto Blackboard, and that video is going to be a British guy talking about AC current using demonstrations that I can't use here. But just keep in mind what he's talking about, his frequency, is he's going to be talking about a frequency, I believe, in 50 hertz. All right. But that's over in the European model. Just remember that we in the United States use 60 hertz. On ships, we use 60 hertz. All right. So a voltage with a positive phase angle starts after the peak, right? A voltage with a negative phase angle starts before the peak. All right. So let's talk about actual wiring. Hold on, let me go again.
Go back to the last slide.
Yeah. Is Blackboard going to be down for you guys? Okay, because this should be up on Blackboard. So single phase 2-wire AC, we have a live wire and we have a ground or a neutral wire. All right. And basically what's happening here is that this one A is going to be, actual live current. All right. And we have our ground or our neutral. So we have our effective value, which is at 120 volts. We said it's not to its peak. All right. Live terminal A raises above and falls below the ground potential. So our ground is always going to stay and be at the ground level. It's going to be at 0 volts always. All right. A is going to be going up and below. So it's not going to be changing from A to N, but A itself is going to be changing its current. All right. Now that is a single phase 2-wire system. So if we go to a single phase 3-wire system, what we would have here is 3 wires. We have live wire A, we have live wire B. We still have our ground of neutral. All right, so we still have 0 volts there. So live wire A rises and falls below the ground potential. So A is going to follow on this track when I'm drawing in green here, whereas B will be on the yellow track here. Let's not call it yellow because that's going to be hard to see. Do black. All right, and this is going to be B's track here. And that's what we have is the difference between we have a single phase, which was just 1 wire going up and down with it. Now we have 2 wires that are going to be in basically in opposition to each other. Now our effective value from our ground for A is 120 volts. For B, it's negative 120 volts. So basically our total voltage between A to B is going to be 240 volts. So 3-phase 4-wire AC. So we have A, we have live wire B, and we have live wire C. Now, all of these are 120 degrees apart from each other. All right, their peaks are 120 degrees apart. And what we're going to see here is a lot more of a constant voltage going through it. All right, so from A to its neutral is represented by this yellow line here. From B to its neutral, we have this green line. And of course, from C to its neutral is this blue line. Each one of those are going to be 120 volts, their effective value. So our phase voltages of voltage A to N, voltage B to N, and voltage C to N. But then we also have our voltages from A to B, B to C, C to D. Not C to D, A to C. There we go. We have our line voltages. All right. So we have our phase voltage and we have our line voltage. Just how we had our line voltage from A to B in the last slide was 240, but our phase voltage was 120. All right, and here our phase voltage is still 120 because we're going only from A to N. But if we look at our line voltages from B to A to C, and C to B, those are going to be a lot higher. So three-phase, four-wire AC. Dual voltage, which is the voltage of L, is equal to the square root of 3 times VLN. All right, so we have some examples for that. We have our voltage Ln is 120, and then the voltage L is 120 times square root of 3, which is equal to 208, which is Maritimes College. All right. Then we have our industry facilities. Those are going to be existing at 480 volts. And then our Con Ed distribution is going to be existing at 4,160 volts. All right, and that's our line voltage that we were looking at. All right. So if we look at domestic distribution, now these are always going to be, the numbers may change, but the idea is always going to be constant. All right, so you have your telephone poles, and the topmost wire at the top is going to be your ground. Then you have your 3 live wires. We're going to have a transformer. It's going to be a 10-to-1 step down. One side of the transformer is going to be hooked up to one line. The other side is going to be hooked up to the ground. And we're going to have 3 wires coming off, one of which being the ground. It's a 3-wire single phase. So each phase is going to be 120 volt from its ground. So this is how you would see those big white cans up on the top of telephone poles. Those are your transformers, all right, where you have your main power lines that are handling your high voltage all the way up on the top. And then you see these smaller cans and then smaller wire coming off of it and running to several houses. This is how it's actually going to be happening. You're stepping it down from your high voltage using only one of those wires, and it's going to be splitting out to multiple houses. All right. So those wires come off of that transformer. They will go through a meter. This is the first thing it hits before it actually goes into your house. So this is how they're going to be getting your kilowatt per hour meter. Now we're going to go into our domestic distribution box. All right, our circuit breaker panel. So we have 3 wires in there. We have our ground, which is still physically attached to the ground all the way on the pole. All right, we have our 2 live wires. We have our main circuit breaker. Those are symbols for circuit breakers. Sometimes you'll just see them as this, drawn simply. All right, that's still representing a circuit breaker. And another new symbol that we have here is a ground. All right, that's the symbol that I just circled there. That's symbol for ground. So now we have our main circuit breaker. We're going to branch off of that. So if you have one going to your kitchen, you have one going to your bathroom, your refrigerator, washing machine, everything like that is going to have its own separate branch and its own separate circuit breaker. All right. And each branch is going to have a live wire and each one's going to have a ground. So this will be like a lighting circuit for the dining room. And then you can go to your living room, your bedrooms, basement, kitchen. All right. Now, this is what you're going to have, and the difference here is your 240 appliance. And if you notice, we have a double circuit breaker. All right, and that's because in order to get 240, we have to add up two 120-volt circuits. All right, so we're taking power from one live, and we're taking power from another live circuit. All right, and that's how we get to 240. But the last thing we need to talk about is that your outlets will have that third eye there. And we only have two wires right now going into our outlets. Basically, what we're trying to do is we're trying to ground it. And that's an emergency ground almost. So residential and commercial systems are grounded. So if a live wire comes in contact with the ground, a large amount of the current may return to the neutral through the ground. All right. So you'll have a grounding pole in your house. And if you ground anything out on your house, that's your current is going to go through the house and to the ground. It will see a very large amount of current will go through it, more than what this is all rated for. And it will pop open that circuit, protecting pretty much the house. And this is all going to be instantaneously. All right, so let's talk about that little circle right here. So if you're using an electric toaster, a metal toaster, let's say, it has an electric heating element in it, and it's 50 years old, and you basically use the crap out of the wire. All right, you have an exposed wire. What it's going to do is that it's that live portion of that wire is going to make contact with the metal toaster. That metal toaster is now going to become electrified. All right, it's going to have current going through it, and as soon as you touch it, you are going to complete the circuit. So until that moment, all of this current is just building up, building up, building up, building up. And then as soon as you grab it, it's going to complete that circuit. And now it's all going to be trying to return to ground because it wants to go from high to low. All right. So the current is going to flow and the electricity is going to flow right through your body. And it's going to be, the object is to get back to that ground. Fastest way through is through your heart. All right. Now, you will pretty much have a very, very hard time, and it will very much electrocute you. And by the time this thing pops, you'll have a huge amount of damage done. All right. Or it may not pop. I've been electrocuted by household appliances, and it doesn't pop like you think it would. So they made it mandated that you have to have this ground here on all new appliances. And what that does is it saves you. All right, it protects the appliance too, but it mostly is there to save you. And what it's doing is it's going to create a physical ground to the actual piece of machinery. All right, so that third eye there is meant to be only used in emergency. All right, normal current flow is going to be going out of this black wire and coming back into this white one, going into the circuit, going into the white, coming out of the black, and it's all fine and dandy. If this black wire right here gets damaged and you have an electrified toaster, this grounding wire, it's a bare copper wire. Here it is right here. This bare copper wire right here, that is your grounding wire. All right. And this is what's your emergency. This is what that third eye is for. Normal current is going to go through this black and white wire. And this ground wire is going to it's going to have a lot less resistance to flow than your body. So it wants to take the least path of resistance. And this is going to be the least path. All right. As good of a conductor your body is, this is a lot better. So it's going to go through this, especially since this is attached to the point where it wants to go, which is this ground over here. All right. So again, if you have a break in that wire, it's going to electrify the toaster and go through, and it will protect you. All right. And it will pop that breaker because a huge amount of current is going to go through it. So if you if you touch it, you'll be fine. Toaster may feel, hot because there's electricity going through it, and that's how toasters work. You would basically turn the entire toaster into a bigger toaster that is now toasting your hands. But it's not like you're going to get electrocuted, which is good. All right, not being electrocuted is a good thing. So that's residential. But if we talk about shipboard operations, ships don't have grounds. All right. So what we're going to have is that we're going to have an ungrounded circuit. So it's not going to be trying to go to ground. So 3-phase, 3-wire AC is what we have. All right, A, B, and C. We go to our transformers. We come out with 450 out of our generators, and we step down to our 120 volt. All right, and what you could see here is we would use A and B for one lighting circuit. We're going to use B and C for another lighting circuit. And we'll use A and C for our third lighting circuit. All right, all coming from 450 volt, we'll step it down to 120 using our transformers. And then again, we're going to have 3 lighting circuits, but they're going to be all lowercase. So A to B is 120, B to C is 120, and A to C is 120. All right, and those 3 wires will go into a lighting panel. We'll have a 3-pole circuit breaker switch because each one of these wires are live. All right. So as we come into that circuit breaker panel, we'll have our 3-phase, 3-wire feeder. Now, instead of having B as its ground, what we're going to have is we're going to be using the potential difference from A to B. And we're going to be using the potential difference from A to B on this stateroom. All right. But on here, we're going to have B to C, and then B to C over here. All right, and so forth and so on. All right, and we're going to have a 2-pole circuit breaker. All right, and as we can see down here in the animation, all right, no 3 are going to be the same color at the same time. One is always going down on its sine wave, whereas the next one is coming up, whereas the next one is coming up. So in the comparison from each one of them, they're going to have a potential difference of 120, our voltage. Okay? So we have our single phase 3-wire branches. So as I said, the ship is ungrounded for 99% of its things. There's only one point where we have a actual ground, where we want to have that ground, right? It's made that way. The ship is built with it. It's designed in the plants, and what it is it's a ground to find other grounds, right? So it's going to be physically attached to the ship. Be a bolt with a wire that's just screwed right into the hull, welded onto the hull. All right. And this is so that way we can find if anything is grounding itself on the ship. So if a conductor becomes grounded, what happens? Does the engine room explode? Does Y2K happen? Do computers fail? Does the captain just jump off the ship? Really nothing bad happens if one wire becomes grounded. The problem happens when we have 2 wires that become grounded. All right. And 2 wires, I mean by 2 different phases. Either phase A or B are both grounded, or B and C. God forbid if you don't notice it and all 3 of them become grounded, that wouldn't be good. But the thing is that if one becomes grounded, it's not the worst thing in the world. All right. It's when the second one becomes grounding. That's when you have your problem. So let's talk through our ground indication lamps first. They are located in between. If you're staring at basically your TG control panel, all right? You have your turbo generator 1, you have your turbo generator 2, and you'll have 3 lights right here on your main bus with a little switch, little button basically right there, and that's your 3 ground indicating lamps. All right. So these ground indicating lamps will all be lit during normal operation. So normal operation, these things will be all lit up. Everything's fine. All right. And what you're testing for is each one of these are going to come in. You have your A phase, B phase, and C phase. A phase, B phase, and C phase. And each one of these lights are going to represent a ground on each one of those. So if you have a ground on one of the lines, the B phase will go out on the B ground line. All right. If the C phase has a ground, the light on C is going to go out. Why is this happening? Why is one light going to go out? And remember the whole idea is that these grounds right here, they may seem like they're 2 separate points, but the way you have to think about it in your head is if that ground represents the same point in physical space. All right. So this ground, you may as well take a wire and attach it to attach it to line C and move it and put it onto the end over here. You might as well just stick a wire and connect it, because that's what that ground is representing. So if we look at this, a couple things are happening. One, this ground is attached. So now C goes out because there's no potential difference. So if the voltage on this side is the same on voltage on this side, and there's no potential difference to be pulling it one way or the other, that light's going to go out. There's no current. There's nothing for that to light that light. All right. It's the same on both sides. But what's going to happen over on B and A, and this is where it gets interesting, is that now instead of having a ground voltage of 0 on this side, you have a voltage of C. So the power of C is going through the ground and, like I said, attaching itself to the opposite side. So now you have a greater potential difference than from B to 0. You have a potential difference from B to C, which is much larger. So that's why these lights are going to get brighter. All right. And that's the interesting part about this whole piece. So during normal operation, these lights are all going to be lit. All right. So in order to check, because light bulbs go out, and this was more of a problem, 15 years ago or so, before LEDs started really becoming prominent and ships are starting to go towards LEDs, is, light bulbs go out, and they used to go out a lot. So they added this switch right here, just in case before you went searching on a mad search that would end in nothing, if one of these lights was just the bulb died, you wouldn't know. So what they did is they added this switch so it removes the ground. So you no longer have a wire connecting the two ends. You basically opened up the circuit, and now these 3 lights all become on. Now you know you have a ground. If all 3 lights don't come back on, and let's say C remained out, well, just change the light bulb in C, and you're probably good now. All right, that's the point of this ground indicating switch right there. It's a tester to see if these light bulbs are broken. All right. So this is when it becomes a problem. When you have 2 grounds. All right. Like I said, you might as well stick a wire from this ground to this ground. Well, now you're sticking another one from here to here, which means all 3 of those things are connected at the same point, which means you might as well stick a wire across these things, which isn't good. If you only have 1 ground, it's not really much of a danger. Just go find it. All right, we'll talk about finding in a second. But if you have 2 grounds, this is when you're going to have that problem. You might as well, like I said, attach a wire from this run right here to there. And that's how you blow those circuit breakers, and you trip them open and you lose power to certain portions of the ship. Because too much current is going through. You lose B and C. They're gone. All right. So before we go into that, who has an idea of, if you were to have a singular ground, how would you go around finding it? How would you go and locate that ground? You just start turning off machinery at will? What would you do? So in order to find the ground that you'd be looking for, say if you have a ground only on the A phase of your circuitry, what you would do is that it would be a two-person operation, and one person would be with the radio, one person would be standing at the ground indicating lamps, and one person would be sitting at this basically your switchboard with all of your breakers. And you'd go through, and you'll know since it's on the A phase, like we talked about, A may be used on a whole bunch of things, it may be used on a small amount of things, but you'll have a schematic where it will say where the A phase is used. So you'll go to these circuit breaker panels, and you'll start off with your large distribution panels. All right, lighting for the starboard side of the ship. Flick off that circuit breaker. All right, and you ask the guy at the radio standing at the ground indicating lamps, did the light go out? The answer is no. Turn that power back on, move on to the next one. And you start off with your biggest distribution. All right. And then after you locate and you say, all right, the light went back on, we're good. And say you're at your, let's go backwards. All right. So remember, when I said we're hitting these bigger circuit breaker panels, you would be throwing these big switches. All right. That would be one big switch. But there's all these smaller lighting panels in it. So now we've located it down to inside this panel somewhere. The light turned on after I threw that switch. So now we know it's a problem somewhere in here. Okay. So the way we would locate it is like we have to find, like I said, it's A. We know it's A is the problem. Green is B, blue is C. All right. So now as we go through, we're going to go and slowly, all right, we'll flow this switch first. Did the light go off? No. All right. Now we throw this one, and we just keep moving through until we find it. All right. And that's how you eliminate, and you go through and slowly try and figure out where this ground is. All right. Start very, very large, huge piece of information. Okay. So lighting panel for the whole starboard side of the ship. That's not it. You go to this port side of the ship. If that wasn't it, then you go into the engine room lighting panel. All right. And then you go into machinery, and you just keep slowly going through until you narrow it down from the entire ship has a ground on A to, oh, it's only on the AMS lighting panel. All right. Now, where in AMS is it? And then you can actually locate, and get it down to just maybe a small stateroom that you have to check instead of a whole ship anymore. All right. And then there's a question in chat. Isn't there supposed to be a connection with metal and circuit for grounding? So you're only supposed to have, so when you're grounding, yes, it's going to be contacting a piece of metal of the ship somewhere. All right. Like I said, this ground right here is going to have a physical attachment to the ship. These grounds are not supposed to be there. That can be like a frayed wire somewhere. And then that current's going to be going through the entire ship to this location. So we can't follow this. So the problem is this: you're not going to be able to follow all of the runs of all the cables. All right. The thing is that in order to find your ground, you have to start at a larger area and break it down so you can get a smaller area, or maybe one stateroom. It might be in the second engineer's stateroom. Now you can try and find the ground in that room. All right. And going from there, what you would look for is, you would pull open all the lights and you'd look inside the lights and see if anything was sparking in there, if any grounds like that. If you check through everything in that room, basically what you would have to do is that you would have to eliminate where the ground could be. And that's when you would have to, once you check all the equipment, then you can start following the cable in that room. But like I said, you're not going to be able to look at every single foot of cable throughout the entire ship. That's not possible. Not because you just don't want to. It's just not physically possible. You have to cut open spaces. All right. So let's look at our electrical distribution for the TSES. All right. We're almost done here, guys. So we have our MSB, or this is our main switchboard. All right. We have branches that come off, and a branch comes out and goes to a motor controller. All right. And the motor controller's functions are to isolate. It starts and stops the pump or the motor, whatever you're using. There's speed control, there's reversing, and then there's basically an overload protection. All right. You have feeders. A feeder is going to basically another circuit panel, like a circuit breaker panel, and then branches are going to go off to an individual component. All right. And then you can have feeders that will go to another motor controller center. And those motor controller centers will have basically, instead of having a motor controller right next to a pump, you would have a wall dedicated to motor controllers. So you don't have high voltage wiring going all over the ship. All right. Let's go through. So this is what we actually look like on the ship here. All right. So we have our main switchboard. We have our shore power coming in over here. And this is our 450 volt section. So everything in this line is 450 volt. All right. So we have both our turbo generators going onto the line. All right. And then we have our diesel generator. The diesel generator is only going to be running when the TGs are not. All right. We use that diesel generator in port. Okay. But both TGs need to run in order to supply the ship with enough power during normal sea operation. All right. Then we go through a transformer, and that will go to our main switchboard 120 volt section. So it's split. All right. The 450 volt and the 120 volt don't touch each other. All right. So this will go to our lighting, our machine shop, all of our power tools, everything like that. And then if we come all the way over here, we have two circuit breakers that separate our 450 volt main switchboard to our emergency switchboard 450 volt. All right. So we have all of our 450 volt emergency loads. So our emergency fire pumps, all that kind of fun stuff. And of course, we need lighting in order to do anything with an emergency. So again, we have an emergency lighting transformer that goes to our 120 volt emergency lighting loads. All right. Battery chargers, all that fun stuff. So let me erase the ink on the slide. And then we have our emergency diesel generator. All right. Does this layout make sense before I start talking through scenarios or any other questions? Because this is going to be basically the last of it. This is going to be all encompassing of what we just kind of went through. All right. So normal operations looks like this. All right. Both TGs are online. We're in the middle of the ocean. All right. Let's picture that. Now, for all intents and purposes, these red switches here, these red circuit breakers, are going to be closed circuit breakers. all right? Gray is going to be equal to an open, so no current is flowing through, all right? And just like that, we can have our orange is going to be an online generator, and gray is going to be an offline generator. All right. I would have that written down because that will help you through studying on your own. So normal operations of what we have going on here is you have your TGs both online, your DG is offline, normal power is flowing through, or 450 volt is happy, we're sending power to our pumps. Our lighting circuit is closed, we are sending out our lighting circuit on our main switchboard. Both of our switches right there are going to be closed because we are going to be sending power through our emergency switchboard. This is important because we will not have doubled up power. So your emergency lights aren't going to be getting fed off of this main switchboard 120 volt section during normal operation. All right. You're basically feeding your main switchboard to your emergency switchboard, which is going to feed your emergency switchboard 120 volt section. So, all right, so keep that in mind. Your emergency lights are scattered throughout the ship and they're on always. So what happens if we switch generators here? All right, so if we put on the diesel generator comes on. We turn off one turbo generator. We open up its circuit panel. We open up the other one after we turn off the other TG. All right. Now, if we have a problem and our DG shuts down for some reason during this, we do not have any backup DG for normal shipboard operation. And that's what the thing is. It's normal shipboard operation. All right. So if that DG shuts down, boom, something happened. We got water in the fuel. That DG shut down. This is what's going to happen next automatically. From this point forward, it's all automatic. Now, we have lost full power across the ship. We have no power except for our battery loads, all right? So our general alarm, things like that I've talked about, all right? That is what's going to be on board the vessel right now. Let me erase this so it doesn't get confusing. So, a couple things that are going to happen. We have no power, all right? This circuit breaker right there is constantly sensing at this portion of the line. All right. If it senses no power, this is what happens next. All right. Senses no power. It pops open. All right. So that circuit breaker is now open. It has no physical contact to the main switchboard. All right. And this is how, when you turn on your eGen, you will only have power on the eGen line. All right. Because this emergency diesel generator, or the eGen, is only large enough to handle a certain amount of load. And that certain amount of load is what's built onto this emergency switchboard. So that emergency diesel generator, the eGen, is going to kick online automatically. This circuit breaker is going to stay open. It's going to close the circuit breaker for the emergency switchboard. And now, boom, we have power to our emergency lights. We have power to our emergency systems. whatever that may be. Big thing to keep in mind here. This circuit breaker right here is still closed. The only one that popped open is this one right here. All right. So now, if we want to, basically, if we put on our diesel generator, we got that running. All right. It was just a hiccup. Everything's fine. We could put it back online. All right. Now, we put it back online. We put it onto the main bus. Remember, the emergency switchboard and our main bus are still separated right now. They're two different entities. And we now have power going through our main switchboard from our diesel generator. This circuit breaker right here is now sensing power on this line. And the only reason it can do that is because this circuit breaker stayed closed. So what does it do? It'll shut down our EDG, and we can go over and manually close this circuit breaker, and now we're back to normal operations. All right. Any questions on that? All right. So